Hey, so welcome back, and this is another daily code problem. So today it's called Successful Pairs of Spells and Potions. So let's take a look at it. So don't want to reveal the answer just yet, but it is a medium level question, and what you're given is two arrays here, spells and potions, and then you're also given a integer called success. And basically what you want to do is you want to hit this number or higher, so 7 or greater is your goal. And to hit this goal, we want to find any spells or potions that will produce a value that's greater or equal to 7. And you can produce this number by multiplying a spell by a given potion. And so you want to say, okay, if we're given this spell 5, how many potions in this potions array will produce a product that's greater than 7? And so you can multiply 5 by 1, which is 5, so not greater than 7. 5 by 2, that is greater than 7. 3, yes. 4 times 5 is 20, so yes. 5 times 5 is 25, and that's also. So what you're going to output is for every every spell in the spells array, you're going to give a corresponding number of all of the combinations of spells and potions that will produce a product that's greater than or equal to 7. And so it's 4 in this case because, well, 5 multiplied by any of these 4 numbers will be greater than or equal to 7. And then for 1 in this case, well, 1 multiplied by any of these numbers are not greater than 7 or equal to 7. So it's 0. And then for the number 3, well, there's these 3 right here. So yeah, so that's basically how you would answer this first example. So to write out an algorithm, or how we would actually be able to solve this, is I thought it was very intuitive. What I did is I thought, okay, naturally the way I would want to look at these is I'll probably sort this potions array, because I already know I don't really need to sort through these values because I'm going to want to do some repeated work for every single one of these spells. So I know I'm just going to have a for loop that iterates through each of these spells and wants to produce a value. But then from here, if I sort these, then, and this example is great because it's actually already sorted, then it's much easier to be able to tell which values will produce a result that is greater than or equal to 7, because you can run a binary search on it once it's sorted, which can say, okay, say I start here at 3 and say, okay, if this does produce a value that's greater than or equal to 7, then I know I need to kind of consider just these values on the right. But say if it's not, it allows you to keep kind of having your search space when you're looking for the values that are greater than or equal to it. Because basically once you hit the point where, okay, it's at this point exactly at 3, for say the number 3 that we're considering, where we know, okay, so if this, anything to the left of it does not create something greater than or equal to 7, but everything past this point does, then we're basically just looking for what is the very first index that will produce a product that's greater than or equal to 7. And once we find that index, we know from that index onwards, every index past that point will produce that. So you just need to search for that very first position that will create that 7, because it's sorted. Everything past that point will produce a product that's greater than or equal to 7. And so, yeah, that's basically the algorithm. It's going to have a time complexity of n log n, and the bottleneck here is sorting it, which is n log n, and then basically you're going to iterate through every one of these spells, and then you're going to iterate through the number of potions. And so this will be n time, and then since you're searching through the number of potions, this will be log n time. Okay, and so now the difference is okay, well, the number of spells and number of potions can vary, so really it's n times n log time. And so really what this algorithm is to sort the potions, it would be m times log of m. And then to actually perform the algorithm itself, it's going to be iterating through each of these spells. And then for the search space, it would then be, okay, for every spell you have to iterate through it, and then a log of m for the search space. So I'm not sure what the bottleneck is here. Naturally, if the number of potions is bigger, then the sorting will be the bottleneck. But if the number of spells is greater, then that will be the bottleneck. So yeah, so basically this is the time complexity, and the space complexity is just O1 since we're going to do everything in place. So yeah, let's get ahead and write out the algorithm. So first thing is we want to create our kind of resultant array. So everything's going to be initially set to 0, and we want a cell for every single spell. And naturally we're going to be returning this pairs array at the end. The next thing we're going to want to do is sort our potions array. And then we're going to want to iterate through each of our spells. So for every spell in our, let's see here, in our spells array, sorry. And then we're going to want to set the current result at this index. So we'll want to then enumerate these spells, and this is how in Python we can get the current index. Great. And so from there, what we're going to do is we want to say, okay, how would we search this space in a log of n time? Well, naturally we'll be using binary search for that since it's already sorted. And so to do that, what we're going to do is we want to search for any number, or really the first number that will produce a value that's greater than or equal to 7. So what we want that number to be is, let's say, required strength, we'll call it, is equal to the target that we're trying to obtain, which is called success, which is passed right here in our parameter. And so that's the success number that we need. We just divide that by our current spell. And so then we know, okay, the required strength that we need to obtain this number is just that number divided by the current spell that we have. So therefore, required strength times spell will equal to our target success number. And so because this might kind of produce a decimal or like a floating point number, we want to take the ceiling of it and not the floor. And so from there, what we're going to say is, okay, we want to find the first position in our array, in our potions array, that would produce this required strength, and anything past that is our sum. And so is the sum of like the potions that will give us our target number. And so you just say, okay, let's take our required strength, I believe. No, we're going to take the length of our potions. And then in Python, you can do binary search and search for a index in a particular array. And so you can do, I believe it's called bisect left here. And so this will say, okay, find me the index where I would actually insert this value. And so if we want to insert our required strength, and it's called bisect left, there's also right. And this is just saying, okay, give me the index to the left of where we would insert this value. Because say if this value is actually already in the array, then just give me the insert position to the left of it. Great. So from there, we just subtract our the length of the array, because that will take the subsection on the right-hand side of, okay, these are all the values that will match. And naturally, we'll also want to pass in our potions array for this. Great. Let's try running that. Accepted. Oh, I accidentally passed or logged out there. Let's try that again. So compile and let's run that. So great, yeah, so that's today's algorithm. I thought it was fairly intuitive. The first thing I thought of was, okay, it's a lot easier to do this in my own head if I was just, say I was giving like 1,000 potions here. It'd be much easier if I sorted the numbers and then just find the first number that will produce that required success. And then from there, we just grab from that starting index to the end of the index, and any numbers in between will be grouped together and put in our output array. So yeah, I hope that helped, and good luck with the rest of your algorithms. Have a great day.